Good morning, everyone. My name is Tianyu Gao, and I'm from the Graduate Center City University of New York. I'm excited to present our extended abstract in collaboration with Professor Ping Ji on leveraging large language models to identify internet censorship through network data. Let's begin by understanding the motivations behind our research. We are witnessing an intensification of internet censorship measures worldwide. Governments and other entities are employing increasingly sophisticated techniques that evolve with each passing day to control the flow of information. Existing censorship measurement platforms like Uni and Censor Planet are doing a great job of collecting vast amounts of network measurement data on a daily basis. However, much of which remains unexplored. As of April 2023, Uni has amounted 1.38 billion measurements, and the Censor Planet has collected a staggering 78 billion measurements. Last but not the least, within this data collected, there are rich semantic contents, such as DNS and HTML responses fetched from the network props, which can provide valuable insight into the nature and the extent of censorship. Traditionally, internet censorship detection relies on rule-based detection methods, using manually designed rules and the censorship fingerprints to distinguish cases of censorship. These rules are designed by human experts, based on known patterns and behavior associated with censorship activities. However, rule-based approaches are becoming increasingly ineffective because they require significant human expertise, are labor-intensive, and most importantly, cannot detect new censorship methods not captured by the existing rules. Given these limitations, it's clear that a new approach is necessary. So let's explore the current trends in censorship detection, namely the learning-based approach. The learning-based detection methods utilize machine learning models to automatically discover blocking rules or patterns of anomalies within the data collected by censorship measurement platforms. Unlike traditional rule-based approaches, machine learning models learn the rules of censorship from the data itself, making them more adaptable and robust. Learning-based methods excel with large data sets. The more data they are trained on, the better they become at detecting complex and nuanced patterns. This capability is crucial for identifying sophisticated and evolving censorship techniques that may not be captured by static rules. Let's look at some recent works of learning-based detection which have shown promising results. For instance, in 2023, Duncan and Chen present two novel learning-based approaches for detecting censorship using datasets from Censor Planet. First, they use a sequence-to-sequence autoencoder to capture the structure and order of network reachability data, employs a densely connected multi-layer neural network to estimate the probability of censorship events from the inferred latent features. Second, they encode network reachability data as grayscale images, classifies these images as censored or not, using a dense convolutional neural network. Both approaches successfully detected instances of censorship missed by rule-based approaches. Brown et al. In 2023 utilized both supervised and unsupervised models to detect DNS-based censorship from satellite and Uni datasets, training supervised models on expert label data for high accuracy and using unsupervised models to identify new censorship anomalies. Cai et al. Utilized decision trees and a novel clustering approach to analyze data from Censor Planet and use Uni dataset as on-the-ground confirmation, effectively identifying blocking patterns and providing insight into censorship dynamic at both local and national levels. These examples demonstrate the potential of learning-based methods. But what if we could take this a step further? This brings us to the potential of use of large language models in this domain. Now, let's imagine you are faced with these challenges in a field of research. You have vast amounts of unlabeled data, rich semantic content within the data, complex and evolving patterns that wait to be discovered, and the need of scalable and adaptive analysis methods. What is the last time a field faced the same challenges? Does that sound familiar? The challenges ring a bell to you? Indeed, the field of natural language processing has faced similar challenges. The NLP deals with vast amounts of unstructured, unlabeled data, rich semantic content, and complex patterns. So what was the solution that really advanced the growth of this field? Not only in the field of NLP, but also artificial intelligence in general. Yes, the answer is large language models. Large language models have revolutionized NLP by providing powerful, scalable, and adaptive tools for analyzing and understanding natural language text corpus. They can process large datasets, extract semantic meaning, and adapt to new patterns and context. Our research is built on this foundation, adapting large language models to analyze network reachability data to uncover patterns of internet censorship with precision and depth. The rationale for this approach is based on the similarities between the scale, structure, and semantic richness of NLP corpora and censorship measurement data. Just as large language models have transformed NLP, I believe they hold the potential to revolutionize the field of internet censorship detection. So how does large language models could potentially solve these challenges? First, let's consider the adaptability of large language models. One of their key strengths lies in their dynamic learning capabilities. Large language model can continuously learn and adapt to new patterns, keeping up with evolving data and techniques. Additionally, through transfer learning, these models can be fine-tuned with minimal labeled data to adapt to specific tasks quickly, making them versatile in different contexts. Next, let's look at their ability for pattern recognition. Large language models possess deep learning capability that enable them to recognize complex patterns and anomalies within large data sets. Moreover, they can differentiate between normal and suspicious activities by understanding the context. Large language model also excels in semantic understanding. They are capable of rich semantic analysis, interpreting the meaning behind network in a way similar to understanding human language semantics. And lastly, let's not forget the scalability that large language models bring to the table. They can efficiently process and analyze vast amounts of data, which is crucial for extensive network monitoring. As we look to the future, there are several key areas we plan to focus on to further advance our research. First one is datasets. Our preliminary choice of dataset is the IC-Lab dataset due to its detailed data collection across all levels of network stack. Although the IC-Lab is not currently active and may not have the same scale and coverage as UNI or SensorPlanet, its detailed context-rich data offers a valuable playground for large language models to explore, making it a good starting point for us. To further enhance the accuracy of our findings, we plan to manually create a label dataset for fine-tuning the large language model. This label dataset will include known instances of censorship by cross-referencing results obtained from IC-Lab with data from UNI and SensorPlanet. The implementation, we plan to transform network measurement data into a format suitable for large language model analysis. Our preliminary choice of model include BERT and GPT-3 due to their strengths in understanding and generating context, supported by extensive research. Further research will be conducted in this area. And finally, the evaluation metrics. It's extremely hard to evaluate global censorship event discovery, as censors would never disclose the measure they impose to us. To overcome this, we plan to use a combination of methods. First, we will cross-reference our findings with data from UNI and Sensor Planning to validate our model predictions and reduce potential false positives and negatives. Second, we will employ both qualitative and quantitative assessment by comparing our results with known instances of censorship documents in academic literatures and the news reports from the Internet freedom organizations. Additionally, we plan to define new metrics to enhance our evaluation process. The ultimate goal is to explore the potential of large language models to process and interpret extensive complex network reachability data, thereby enhancing the accuracy and scalability of censorship detection. This work is supported by Google Cyber NYC Initiative Awards. Thank you to the anonymous reviewers for insightful comments on the paper. And thank you for your time, and please let me know if you have any questions. Goodbye.